everyone. My name is Sella Rafaeli. I am VP Solutions at Web Security, and I work with our clients to help them understand API security. APIs are Gartner's #1 attack vector, and it's very important for enterprises to understand the impact of this new attack vector on them, understand their own vulnerabilities, and figure out a process to detect these vulnerabilities before malicious actors do so. In today's talk, we're going to share the top 10 real-world vulnerabilities that we commonly see on enterprise APIs. We will discuss in depth the technical details of each vulnerability. We will discuss how an attacker can automatically detect these vulnerabilities, how an attacker might exploit it, and the implication for the organization. You may have seen some of my talks in the past. Today's talk is a serious technical talk, and we will be talking about the bits and bytes of each particular attack, primarily at the HTTP level. So lots of protein and metaphorical technical meat in this talk, so put on your hard hat and let's get started. So to give you a bit of background and context, a correct full lifecycle API strategy has three main components corresponding to 3 stages of the API lifecycle. Code analysis for development to find issues at the code level, an API attack simulation to test APIs in both staging and production, to find concrete vulnerabilities yourself, and a traffic inspection, which is the firewall equivalent for APIs, and automatic defender in production against API attacks. So at Web, we use our attack simulator to run attack simulations for our clients around the world. Each attack simulation finds the vulnerabilities in a particular organization's APIs, and this presentation is a summary report of vulnerabilities that we have seen repeat themselves often. So we work with financial institutions, health providers, security operators, and organizations of every type that all have some sort of API. We use OWASP's API Top 10 for guidance, but of course rely mostly on findings in the field. So here we empirically find that some vulnerabilities recur often in APIs, and these are the types of vulnerabilities that attackers will be looking for, and that the defenders should ensure that they are checking for and fixing. This is all empirical data from the field, from APIs around the world. We are excited to share this data as it is the very first practical collection of such empirical findings from APIs around the world, showcasing the actual state of API security in the field. I'll take a brief moment to explain how an attack simulator works. So if you have your servers and your enterprise APIs, you're serving maybe a few domains. Each domain has a list of endpoints and routes. Each route reserves certain parameters. Basically, you've got your definition of how your API is supposed to work. So what the attack simulator does is it takes as an input a definition of an API to test or attack and creates thousands of variations to cover any and all possible attack scenarios. Since the API is a formally defined interface, it is very amenable to formal variations. So for example, the first class of variations could be fuzzing attacks, where we try and change one at a time every single parameter for every single route into every single type of data. A good attack simulator would execute many different classes of attacks, just starting with fuzzing, but this is enough to illustrate the strategy. The attack simulator then executes each of this list of variants against the API and finds the attack variants or vectors that succeed from an attacker's point of view or the points of failure from a defender's point of view. So, for example, one variant might be calling the post login route, changing the username into an array and the password into a null, and analyzing the server response. In this case, a 500 HTTP status response and a stack trace and server version in the response means we have found a vulnerability at the API level. So, without further ado, we present Web's API Top 10 vulnerabilities. You are encouraged to play along and see if you can guess what's coming up. As mentioned, we want to make sure everyone understands each of these vulnerabilities and how to detect them, both as a defender and as an attacker, and how to fix the issue. So any questions, especially technical ones, let's discuss during or after the presentation of each vulnerability. The first vulnerability is routes with no authentication. So here we have an illustration to understand what's going on. On the left, we have our attacker. On the right, we have the servers with the dotted line representing the API. We have a white arrow representing the request and a red arrow and red highlights representing the problematic aspects. So here we see an example of a user calling for a route that returns the profile of user number 123 without supplying authentication, and yet the server still returns the payload with the information about the user and an HTTP 200. So clients are able to successfully request data about users without supplying authentication, obviously a very big problem. This is especially prevalent with organizations that have microservices environments or a lacking strategy of making sure all their routes go through an API gateway that enforces the same authentication middleware. One issue that security teams struggle with is visibility into what routes they have and what authentication is implemented on each route. This is the most basic issue of API security, but it is surprisingly prevalent and obviously easy detectable and exploitable by attackers. Any attacker with a good API attack tool can trivially scan the APIs to find which ones respond even without authentication. One example we have seen in the field is of health providers with routes with no authentication exposing the private details of clients, obviously an egregious breach of privacy for their users. Are there any questions? If there are any questions about this particular vulnerability, feel free to write them in the chat and we will address them. Common API vulnerability in the wild number 2 is the poster child of API security. It is broken object level authorization, formerly known as IDOR, and today affectionately nicknamed BOLA. This vulnerability perhaps best illustrates the specific issues that beleaguer APIs from a security perspective, and why API security is such a different beast from an enterprise perspective. So a BOLA vulnerability is one where the server is, first of all, correctly checking the authentication of an attacker. That is, a correct verification is done on the incoming HTTP request that the caller is indeed a known user in the system and not an anonymous request. However, the malicious aspect of an attack on this vulnerability occurs when the user is authenticated but is asking for a resource that does not belong to them, via, for example, modifying the ID of a route. So for example, in this example, user with ID 123 can call the route for the data for user 456. User 123, the attacker, supplies the appropriate authentication, so the server seems to think all is well, but they are actually asking for information that belongs to user 456. This is where the problem is. For every private resource, a server should verify not only the authentication, that we know who the calling user is and that they are a legit user of the system, but that the resource they are asking for is one that they are authorized for. This is, of course, the difference between authorization and authentication, and the nuances of these security aspects are the ones that a developer might oversee and leave the route open for abuse. So in the example presented here, we have the attacker make a call, the server correctly authenticates them as user 123, but the server does not enforce correct authorization and allows user 123 to retrieve the data for user 456. The implication of a BOLA attack is that the attacker can access any other user's data, which in turn means they can access all users' data, which effectively is the equivalent of a complete database dump of all the users' data. All of this from a single missing verification step, a simple if in the code. This is a good illustration of the danger posed by insecure routes and why API security is such a big deal. One example we have seen in the wild with this is with a well-known company in the, let's say, traveling space, which had a route as presented above with a target user's ID as part of the route. Once we detected the VOLA vulnerability, we could quickly iterate over and pull all data of all users, passport pics, ID cards, bank statements, disaster. It is also worth mentioning that using enumerable IDs as part of the route, in this case 123 or 456 as the user ID, this is something that was popularized back when REST format for APIs became the standard, makes attackers' life much easier because now targeting other users or even enumerating over all users' data is quite easy. Vulnerability number 3 is lack of proper rate limiting. So one large communications company we worked with had a route for reset password, which sends a 4-digit PIN to the configured phone number, and the user should enter their PIN to log in and reset the password. The attack vector here is that a sophisticated attacker can simply try all possible options. So as an attacker, you automatically iterate through all the options, and within a few seconds, you will hit the correct one and successfully get the response that allows you to take over the target's account. The remedy for such an attack is called rate limiting, in which the server limits the number of calls by a specific criteria to make sure attackers cannot simply brute force their way in this way and guess passwords, pins, and so on. There are a few additional important aspects specifically about the rate limiting vulnerability. One, the defense for rate limiting does not exist by default. So even a bug-free implementation of an API is not immune to rate limiting attacks. It needs to be consciously added as a defense layer of your API. Number two, rate limiting, when done correctly, must be route specific. In the example above, it is advisable, for example, to limit up to, say, a single-digit number of attempts before forcing another reset. In a more general case, it is advisable to match the rate limiting strategy to the semantics of the route. You can limit by IP, by number of tries per second, by number of tries per day, and so on. Issue number three, rate limiting via a cache layer is important both for applicative defense, such as brute forcing, and as a mitigation strategy for denial of service attacks based on amounts of traffic. And lastly, it is important to understand that a sophisticated denial of service attack can try and bypass even rate limiting by using a distributed attack source. In other words, 1,000 different attack origins, attacking using a low and slow approach, so each individual attacker is not detected and blocked, and targeting vulnerable and or particularly slow routes, often file uploads, payment routes, or routes that have less parallel computing ability. So really, rate limiting and rating attacks are a world of their own, but the very basic vulnerability that we see the most is complete lack of any rate limiting, which makes it trivial for an attacker to brute force any route which receives an enumerable or iterable input. Or in simpler words, if we as attackers can reasonably guess something, we will. Next attack is particularly pernicious and very hard to detect other than when it just happens. Number 4 in WIB's list of top 10 API vulnerabilities found in the wild is broken resource limiting. So imagine you manage users and each user can post a note to their own profile or whatever. The attacker can create 1 note, then 100 notes, and then 10 million notes. If the server has rate limiting, the attacker will simply slow down the approach, but set the attacker to gradually and eventually slowly write more and more notes. When we call the route to pull all user notes, the server will naively try to fetch the n+1 notes we have created for the user, in this case resulting in fetching 10 million notes all at once, which will cause the server to crash or at very least hang jam in various parts, including fetching from the database and returning the data to the client. So while everything in the implementation might look naive, the end result is a route that can cause a denial of service on the server. We have seen this vulnerability just about everywhere. Almost all APIs have some sort of one-to-many resource relationship, and similarly to rate limiting, if the server does not implement active controls to mitigate this potential problem, in this case, some sort of server-side pagination of the data, calling this route will trigger the denial of service vulnerability. Call this endpoint multiple times, and you have a guaranteed denial of service. We have a question in the audience from Chuck. Chuck asks, so the key difference between rate limiting and resource limiting is the velocity of the operation, correct? Slow attacks that eventually consume available resources, leading to denial of service? That's an excellent question, Chuck. What I suggest is let's review the next vulnerability, which is indeed resource limiting. Oh, sorry, we just talked about resource limiting, my bad. So yes, the difference between rate limiting and resource limiting is that rate limiting talks about the amount of traffic that is coming in, the rate at which requests are moving in. So for example, if you send 10,000 requests, one after the other, trying to send them as fast as possible in order to either guess an iterable value or overload the server with traffic, this is a rate limiting attack. Whereas a resource limiting attack is one that is based on the amount of resources within the server and the server's ability to handle large amounts of data effectively and gracefully. Any server can handle 10 million, any server that can handle 10 million notes needs to do so in a paginated strategy rather than try to do everything all at once, because there is, of course, limits and bottlenecks in fetching and displaying such amounts of data. So on to vulnerability number 5, which is public external resources. This vulnerability has to do with modern systems that rely on external services for things like file hosting. Hosting user data on an external resource is tricky in terms of security and very error-prone. So what we often see in this particular case is a server that receives, for example, some file upload, and then stores this item on a third party, like Zendesk or Amazon's S3, which exposes a URL by which the uploaded file can be fetched. However, the naive solution of returning this URL to the client means that the URL is effectively public, as a direct URL to the external service would bypass any authentication and authorization mechanisms implemented by the server itself. So the user uploads a file, gets a URL. If this URL is leaked, it is now effectively public. Such a leakage is very probable if, for example, the target server implements some sharing mechanism or a URL scheme that is iterable or guessable. So to defend against this particular vulnerability, if you, as a defender, are using such a service, you should run any subsequent requests to ask for the uploaded service, for the uploaded resource, through your server to enforce the authentication and authorization, remember, on the resource to make sure it is only sent to those who deserve it. So resources, in short, should be served from your server, even if this requires an extra step to fetch the resource from an external server, or to find some other solution to make sure that the exposed resources are not publicly available for the whole world. Imagine if you upload some customer complaint and it ends up on Zendesk and the whole world can see it, you as a customer will probably be pretty unhappy. All right, we are moving on to lucky number 6. Hang in there, guys. API security is a serious business full of a lot of technical details. It's tricky, and this is why one of the reasons why it is so dangerous. This next vulnerability, missing input validation, is present just about everywhere. So in this case, what we have is an attacker that simply changes the data type of a parameter in a request, and then sees how the code in the route handler handles an unexpected data type. So for example, in a place where the API expects a string parameter, we try to send an array or an object or a null or a file or something like this. If the route handler does not enforce correct strict type checking for each single parameter, and the reality is most servers do not do this. Perhaps more accurate to say, most developers cannot do this, especially with the proliferation of dynamic languages as languages of choice for the server. There is a good chance that the code will return an error or crash. Now, as attackers, this is exactly what we are looking for. Changing the parameter types as part of a request, so for example, taking the name and changing it from a string to an array, is often called fuzzing. As we saw earlier, fuzzing is a main staple of API attacks and something that many API attackers employ. So a simple lack of validation of the input is a very potent and easy to execute family of attack vectors and vulnerabilities, and is in fact usually the first attack approach used by attackers. A lack of input validation shows the organization is not quite managing its API security properly. It is a broken window, you might say, and a sign for attackers that the defense is low, and also often results in real exploitable information about the stack, as we will see in a moment. The solution is not easy, but it is simple. Be conservative with what you accept from outside, and be liberal with rejecting invalid input with a 400 HTTP status. This is, after all, what the 400 status was meant for. As a general rule for APIs and for life, sanitize everything you consume. As in food, such with HTTP. API security vulnerability number 7 is excessive code exposure. Here we talk about situations where the API is exposing perhaps a little bit too much of the code with no benefit for the organization and with potentially dire consequences if the person exposed to this information is an attacker. If I remind everyone in the audience that if you have questions or comments in this workshop, you are welcome to share them with me and with the crowd, and we can discuss. I myself am very excited to be at the forefront of this API security research because API security is really the new cloud security, right? Everyone that has a server in the cloud or a server that can interact with the cloud has an API, and APIs are such a potent attack vector that as a community, the way we mature and develop a shared language about API security and the different types and techniques of attacks and vulnerabilities is really making all of us safer. So this is an exciting time to be involved in the API security space, and it's exciting to work on it with everyone in the crowd. So back to the material. In this vulnerability number 7 with missing input validation. Oh, sorry. So we have a mistake in the title here. We're talking about number 7, excessive code exposure. We have an issue with the title here. Issue number 7 is excessive code exposure, and this vulnerability has to do with how the API behaves after, or rather when, it crashes or errors. The diligent security and development team will be aware that mistakes inevitably happen in a code base, and errors and crashes will happen in your code base. So the question is, do you handle them gracefully? Let's, for the benefit of future generations watching, let's quickly fix this into, here we go. So once again, this vulnerability is about what we do after a crash. How do we handle them gracefully and not expose too much information to our attacker? Crashes often have chaotic and unforeseen consequences and are prone to revealing internal stack traces and server versions. Sorry. Let's see. As Chuck points out, any extra information given to an attacker is too much information. So how do we avoid this situation where we reveal internal stack traces and server versions which themselves might contain valuable attack information? One thing we saw with a large public energy provider we worked with was a route that, upon a fuzzing attack, crashed, sent an uncensored stack trace that gave the server version and stack trace that gave us exploitable CVEs on the server and stack, like the log4j family of Java-based attacks. So regardless of what causes your error, you want to make sure you don't include your stack trace in the response. Most frameworks have some outgoing middleware that can help modify the response to ensure that in any case in a production environment, no stack trace is returned. The stack trace is returned by default, after all, to help the viewer, in case it's a developer, understand what happened with the bug. And in the case of a crash, of course, we don't want to volunteer this information to an attacker. A defender is much better off returning a nondescript something happened to the caller and leave the diagnostic information internal. Web API vulnerability number 8 is coming up. Stay alert. The attackers don't rest, and neither can we. This vulnerability is about running servers, code, and libraries with known vulnerabilities. So in the previous vulnerability, we saw how exposing this information to the attacker makes it trivial to exploit once the attacker knows what they're targeting. But of course, running a vulnerable server and relying on the attacker just not knowing how to exploit it is still just as vulnerable. See, I have a typo here, so one moment, please. I will fix this. Sorry, guys, for the delay. 1 second, and we will be back. All right, we talking about vulnerable server and stack. We saw how exposing the information to the attacker makes it trivial to exploit once the attacker knows what they're targeting. And old servers with known CVEs are vulnerable to a payload with specific maliciously crafted payloads. One example of this is the Log4j family of attacks, which target Java servers and libraries, and by simply including a malicious payload, grant the attacker the ability to execute remote code on the server, which is simply game over. So it is crucial, it is the ABC of security to make sure you are not running old, vulnerable servers and libraries. Attackers, even without prior leaked information about exactly what server you are running, can often just run an automated process of trying to inject payloads. After all, there is a practically limited number of server versions you might be running, a list which is quickly further narrowed down by public knowledge of your stack, which is basically public information via your careers or hiring page. So as an attacker, I check your hiring page, see you're hiring for Java, point my attack simulator at your server, and can try all the Log4j family of attacks and all other publicly known CVEs for old Java servers. If you're running an old vulnerable server, there's a good chance we can get in. Again, as we have seen with this particular pattern of enterprises all over the world, we've seen this particular pattern with enterprises all over the world. If you've ever wondered why it is so important to upgrade old servers and services, this is why. They can be detected and exploited automatically, even if your API is otherwise perfect. Vulnerability number 9 is about exposed domains. Exposed domains and subdomains plague enterprises, especially ones that grow larger and older. Over time, more and more services are released, and usually they are not sunsetted, but rather just forgotten. And so many apps, domains, subdomains, and services, many often containing direct connection to databases and user data, remain active, connected with the organization in both data and brand, and pose attack targets that are just as harmful. My personal favorite are domains that are clearly meant to be internal, that are exposed by default to the public. Even with authentication mechanisms still in place, there is no reason why your rnd.org.com should be visible to everyone in the world. It's just asking for trouble. This is why visibility for the security team, done via either code analysis or traffic inspection, is so important. Most security teams don't even have the visibility and knowledge into what assets do they have to defend. The tech for such visibility is supplied by firms like WIB, so it's really a matter of a maturing of the API security market, that now for the first time, securities can get some technical solution for this problem. There are two main vectors to reach such visibility. Either by inspecting the traffic with a tool like traffic inspection, or by analyzing your code with an API security code analysis tool. The diligent security team will employ both to ensure they are covering all domains and routes, including shadow and zombie APIs. Visibility into all of your API routes, each of which is a potential attack vector, is a major pillar of a full lifecycle API security. Who in the crowd can guess what we have for vulnerability number 10? Let's see if you guys can guess. We'll give you a few moments. Anyone? Okay, I will tell you guys. Vulnerability number 10. Well, one moment. I see good guesses from the crowd, but actually there's a much larger problem. So mass assignment and forgotten accounts are indeed big problems, but there's one problem that is even worse. And this problem can be summarized as a lack of an API security defense platform. Sadly, most companies' APIs are basically completely protectionless, or at most have obsolete technology like WAFs, which only defend web applications and not APIs. Now, the challenge that modern enterprises deal with are attackers that are not your individual lone hacker, but rather funded, experienced groups of nation-state actors, as evidenced by the recent geopolitical flare-ups, or ex/paramilitary groups. I can speak to this from personal experience, as this is reflective of WIB as well. Our teams come from a lot of military experience of API security, both offensive and defensive. We've been doing this type of work on a national security theater, which constitutes, as in many military verticals, field experience that is hard to replicate in the civilian arena. These are teams that have worked together, that can build their own tech. These are teams of professional attackers. At WIB, we wear a white hat as we assist enterprises in staying secure, but our counterparts all over the world are similarly maturing from individuals to state or privately funded professional cybersecurity warfare units that are commercially available for financially motivated attackers as well. If your enterprise is targeted by a nation state or an ex or paramilitary cybersecurity offensive unit, relying on the diligence and goodwill of your developers, who are also responsible for the API correctness, robustness, maintainability, and performance of the code, is a losing proposition, and one that CISOs and security executives are gradually realizing. Defending nation-state abilities requires a military-grade defensive platform. The API security space has seen an arms race that is only escalating, especially in terms of automation and detecting vulnerabilities. Leaving your APIs exposed without a defensive full lifecycle API platform is like riding into combat with no body armor. Brave, but stupid. So, this has been a deep review of the most common API vulnerabilities found in the wild today, and ones that likely plague your organization. It's nobody's fault. API security is hard, but that's no excuse. By now, most people in the field know that API attacks are the #1 attack vector. At the least you can and should do is make sure you have implemented a full lifecycle API security platform as soon as possible. Thank you everyone for attending this talk and participating. If there are any last-minute questions, this is a good time to write them in the chat. And if not, we will thank you for your attendance and hope you guys make sure your APIs are secure. So have a great day and stay API secure.